Thanks a lot, Mike. Appreciate it, having us here. Thanks a lot for coming in. We're quite excited to be in Africa. For me, that's the first time actually being in Africa. So thanks for coming and listening to us. And like Mike said, if there are questions, please feel free to ask us. Happy to answer your questions. That's what we're here for. We just use the presentation as a rough guide to go through, but we can make this interactive if you guys want to.
So as part of this, we developed and testing this product, and we were launching it in Australia. And I said, Australia is kind of seen as the leader. I guess it is, but you guys are also leading in South Africa. You got products, and I walk down here and I look at these products around here. These are world class. There's no question about it.
And we've seen work here now. It's fantastic. We went through the workshops in the last few days, met people, saw installations, and I cannot say that you guys are far behind Australia. I think it's pretty much on par with what you do, what Australia is doing.
Yeah. So I don't think you should look and say, oh, they're doing it better than us. Well, you're doing some things better than you, but you're also doing things better than most of the rest of the world. So we came up with this idea, and I think maybe I should introduce Heiner, because Egon started, and I want to introduce Heiner because many of you won't know who he is, but it started because I'd been asked to build a few overlanders for some people. I don't do it anymore, but at the time, I'd met Heiner. He'd done some work on my troop carrier, and he built this beautiful electrical system with all wiring and everything, and the little inverter, and it's beautiful. And I said to him, could you take that and standardize it? So in other words, you just spent 2 days doing that.
Yeah, you wanted to export them into the USA. You said, how can we export wiring into the USA?
Because they were so crap at it. They were so bad at it. So then you said, I've got a drawing, because you were thinking along the same way. So that was the birth. He said, there's my drawing. There's my idea. Could we make a product out of it? And it was kind of, I don't know, maybe. So we did. So now we're at the second generation of 5 years of development testing. We've got about 1,000 of our primary units around the world, and we've learned a massive amount. And I said, hang on, we need to bring it here because you guys could really use it. Now, it's not that your electrical work is necessarily that much worse than anybody else's, but there's an average, and you're kind of on the average. Now, you would think that Australia is above that average. No, not really. There are those places that do it beautifully, really, really well, and there are a lot of them that often the big branded shops, because they're not specialists, well, they do electrics quite badly because they're not specialists, but they'll do their products quite well because they're specialists. Same here, same in Australia, same in the United States. So the whole idea behind the Egon products was to take that, and Heiner will go through it technically now, that weakness, if I can say it, that middle bit. You get all of these beautiful products, Victron and Red Arc and Enerdrive and all the nice products. Connecting them is the problem. The products don't normally fail, it's the...
We get to that, Andrew. It's the installation.
So that's the kind of birth. Now, just before I hand it over to you, Heiner is a mechatronics engineer, University of Berlin, was it?
Bochum.
Okay. And then worked with Mercedes-Benz, AMG, doing electrical installations, programming systems and things like that. So that's his qualification. You, the rest, know my qualification. And I'm now going to hand it over to you.
Thanks, Andrew.
All right.
I've been running my own workshop in Australia for about 10 years, and I sold it a while back to focus more on Egon. And one of the problems that we found in our workshop was that central part of the installation, we're just building over and over and over again. And it was something where it would have been really good to just go copy, paste, because it did eat up so many hours every time building the same thing over and over again. And I worked in the mining and road construction industry before, fixing machinery. And in those machines, these really big surface miners, they work in the Pilbara, Australia. There's a main switch cabinet in them. It's 2 meters high, 1 meter wide. There's thousands of wires and components in there. And when it fails, it takes about 3 weeks to replace it and rewire the machine. Eventually, those machines changed. And instead of 2 by 1 meters, it was a 1 by 1 meter compartment. And there was a circuit board in there. And if you needed to change it, it took half a day. And I thought, this idea we should apply to the overland, to the installation market. And that's really the idea behind Egon. We go away from wiring things with cables and bus bars and fuses and pre-fuses, and we just put everything on a circuit board, because then it's done in a controlled environment. The power distribution system is always the same. So that's the main idea. What happens in workshops at the moment is usually that everybody who's running a workshop and does electrical installations will always say, we like to do these as best as possible, but the problem is if we do, it just takes too long. And you're usually lucky if you can charge for about 50% of the time that you actually need for that installation, which is a problem because in the end, a business still has to be profitable. And on the other hand, if the DIY people want to install things themselves, they need a lot of knowledge, which a lot of people don't have. And it's not easy to come by as well, because there is no training. There's no training systems anywhere. Auto electricians do their apprenticeship, but they're usually not being taught on how to install battery systems, DC chargers, solar, inverters. And they're also not trained on how to build a power distribution system. Another big problem that workshops have got is to have skilled staff, train skilled staff, retain skilled staff. Usually, if you build somebody up, at least in Australia it's the way, after a while they go, well, I'm either going to go into mining now, or I'm going to start my own business because I've learned everything here, and I think my own business is the next thing to do. So it's very hard for workshops to hang on to their staff, especially the good ones. And another big thing that everybody who's running a workshop will probably find is the after-sales service. If you've done an installation, let's say 2 years ago, you would have done another 100 installations in between, and the customer calls you and you haven't got a standardized system on how you install everything. The customer will say, oh, I'm in the bush, calling you from Starlink. My fridge has just failed. Where can I find the fuse? And you go, oh, 2 years ago. Who was working in the workshop 2 years ago? How did we do things 2 years ago? That's the problem. If you don't have a standardization, you can't remember where it was, because there's just too many variations in the business. Doing all of that with the circuit board, you can have a set layout and say, like, that fuse will always be the fridge. And you can tell a customer, go to that box, take the cover off, change a fuse. How did you go? Most customers can even do that themselves without calling you beforehand. So one of the biggest problems, or the core problems of DC installations that I have found over the years, is that the workshops that are building these systems, they are usually unaware that they're building something that is called a power distribution system. What they do is they connect components together, and you can do that in a lot of different ways, but what's really important is that you think about it from, if you want to think about water from a way that you got a really big pump and you want to channel the pressure coming out of the pump into little pipes, but you have to make sure that that massive amount doesn't burst the little pipes. So you can't have a big pipe, a small pipe, and another big pipe. That doesn't work very well because there's no pressure left in that big pipe afterwards. So the training for that is usually not there. And some people are very good at it, others aren't. Nobody had proper training on it. Power distribution is an issue, and it shouldn't be in the hands of technicians. That's our take on it. Power distribution work should be an engineering task where people make sure it's the right cables with the right fuses going into the smaller cables, and then things work. Because one of the biggest issues in DC installations, 12 volt the most, 24 less, 48 volt even less, is voltage drop. And you guys are all aware of voltage drop, but I think not everybody is aware what voltage drop actually means. Voltage drop is a lot more than just the system not working anymore. If you have got voltage drop, let's say you install a 3 kilowatt inverter on a 12 volt system, and you've got 2 meters of cable going to the inverter, 2 meters of cable going from the inverter back to the battery, and you run it flat out at 250 amps, you probably have about 1.5 volt voltage drop. So that means that you are creating roughly 400 watts of heat. in that system, the voltage drop actually means that you're losing energy. That energy is not accessible for the customer. That battery will produce the 400 watts, and the customer can't use these 400 watts. Over an hour, that's 400 watt hours. That's about 35 amp hours of a 12-volt battery. That is just being wasted, going absolutely nowhere. So voltage drop makes very inefficient DC systems, and the energy that is there can't be used by the appliances. All it really does then is just warm up the inside of the vehicle. And that's not ideal. That's not really what we want. Another big thing is that the faults of DC installations, and please correct me if I'm not right here, this is just my experience from my workshop. Over 90% of the problems that we get, or that we did get in the workshop with the installations, were not due to components failing. It's very rare that a component fails. Usually inverters, DC chargers, shunts, solar controllers, they work quite well. The problems are usually that somewhere there wasn't a lug crimp properly, and the cable started to corrode because it wasn't sleeved properly. There was too much heat in it, or the cable just simply fell out of the lug because somebody heat shrinked it but forgot to crimp it at all. And that's usually the problems that you get with installations. It's not the components, it's how the components are being put together. Either because people don't know how to build power distribution systems properly, or because there's just an oversight of some sort, because in the end, wherever humans work, there's human error, and they'll lead to problems sooner or later. So the role that Andrew and I found for Egon when we said we wanted to export wiring systems, first we thought we're going to build boxes pretty much like the power systems that you can buy from lots of different companies now, boxes with everything in there that you can slap onto a wall somewhere. We said there must be a more elegant way. We can do this so that people can still build their own systems and not just bolt a box onto a wall somewhere. So that's when we came up with the idea of circuit boards. And this is what one of these systems looks like, for example. And the idea of that is that instead of using cables, you just use a circuit board, because a circuit board can be made by a machine. A circuit board can be engineered. All the tracks will always be the same within very tiny tolerances. So this is now a power distribution system that is not handmade. It is made by a machine, and it does it the same way every time. And the components are always the same. So we now got control over the quality of the power distribution system. And we thought this is the best way to do this, because on here, the voltage drop is the tiniest it could potentially be, because there's no crimp going from one side to the other. There is no lug bolted on anywhere. So with this, we can say, this way we can't have less voltage drop than this. So that makes your installation work a lot more efficiently. Andrew, do you want to hand out a few of these?
Yeah.
Just hand out a few products so that people can just play around with them.
Get a feel of one of those. This one is actually enclosed in the mounting stainless steel mounting bracket, but just have a feel of them.
A lot of people shy away from circuit boards because they think of computers. They think like, ooh, can I touch a circuit board? Will it break the moment I touch it? These are not electronic components on there. What this is a mechanical power distribution system. The most electronic part is the LED that comes on when a fuse is blown. Apart from that, it's a very, very solid unit. And you feel it, the weight of those things, they almost weigh a kilo. You could slap somebody over the head with that and then install it and it will still work. And you don't have to worry about touching them and be connected to the earth or something like that. So another good thing about that is that technicians with these power distribution boards can focus on what they should be doing, which in my opinion is connect components together and then commission the components by programming the values that should be in there, testing the installation, and then giving them to the customer. It also takes away engineering complexity because the layout of the system is always the same. What that means in the end is that better results in less time, which brings us back to the very first point where we said DC installations usually take too long. That doesn't necessarily need to be the way anymore, because what happens is that you usually sell your product for a certain amount of money where you know we spent more time on it, and we put more effort into it, but there's a certain amount we can charge a customer before they say, we can't go past this, this is ridiculous. You don't want to pay as much for a house as you want to pay for your vehicle build. But if you can work more efficiently in your workshop, spend less time on it, you get a lot closer to where you want to be as a business and make money and make sure you can stay in business, and from time to time probably have a holiday as well, which is quite important.
Can you show of hands of how many of you actually run workshops or part of the industry? A fair number of you. So the idea, again, behind it was, if you're doing the same thing every single time, you've already touched on this, and a client phones you from the bush, you can say, your fridge, it's fuse number 1. So we also give a huge amount of training, because we figure is that if you're in the bush and something goes wrong with your electrical system, why shouldn't you be able to fix it yourself without knowing anything about electrics? So in the boards, you'll notice there are red LEDs, and that basically is self-diagnostic. If there is a closed circuit in that part of the board, and a fuse blows, the little red LED light comes on. So you can just look and say, oh, fuse 4's gone. That's the sum total of your diagnostics. If you then want to use a meter, the connections are open on the top, and you can check it physically as well. So that was kind of, how do we not only make it easy for the workshops, how do we make it easy for the clients in the bush when they have an electrical fault to go and fault trace it themselves without giving you a call on Saturday during the rugby? That's what the way we were thinking about it.
Yeah, a big part of that for me was also, I used to install a lot of red arc components. And back in the days, the red arc components would be hardwired, soldered, heat shrunk. And the only way to actually get access to the cables and put a multimeter on there was to pierce through the insulation of the cables, which is terrible. Once you've done that, you have to make sure you put a lot of tape around it, put a cable tie on each side, but the cable is never the same anymore. So for us, it was really important to make sure that you have got this one central location where if you want to do fault finding as a workshop, you take the cover off, you take a multimeter, you got access to every circuit, solar voltage, start battery voltage, output voltage of the DC-DC charger, house battery, fridge, lights. It's all there. You just have to sit in one spot with a multimeter, go through, and you can do the fault finding right there. And if it's not there and everything's good, you know, well, from here, I've got a twin core cable to the load, and if the load hasn't got the proper voltage, but the DC hub does, has to be the cable in between. If it's not the cable in between, and I've got power at the plug itself, it's the component. And fault finding is done. It's done in a lot more simple way than that. And you know, I want to touch on the voltage drop again. I think it's really important. If you guys in the workshop want to find out what the voltage drop on your installations is, and it's really interesting to actually understand and play around with that a little bit yourself. The next 3 kilowatt inverter install or 2 kilowatt inverter install that you do, just take the multimeter and measure from the battery terminal directly to the inverter terminal, and then from the negative directly to the battery again. Write down those voltages that you read, because that's the voltage drop over the cables, over the lugs, the crimps, everything that's in the way. And then multiply that by the current that's running through the system, and you get a wattage figure, and that is the loss that you've got in your system. That's how you can measure how well you've built your system. So that's how you can also measure if you have a problem, because if the voltage drop becomes too high and there's a big current draw, it means something will get really hot. It might even get so hot that will eventually get very crispy, and then it might actually catch fire. And that's what you really want to prevent. So it's important to also let your technicians know that when you do the commissioning of a system, take 5 minutes, take long cables on your multimeter, run everything on max performance, measure voltage drop. Because if there's a lot, you will know that you will have a problem in the future. And it's easier to fix that in the workshop before the customer gets their hands on it than it is when you let it go and the customer will actually find the fault and then call you. And it's the same for DIY installations. You want to fix things while you're still in your own workshop and not while you're out camping, where you want to have fun, plan certain things, have a photo shoot, you know, be on safari tour, or whatever you guys do here. We usually go to the beach and have a good time. That's not the time you want to do fault finding. So do a little bit of diagnostics work and check the performance of your system before you actually let it go out of the door. And that way fault finding becomes quite simple. You can be proactive about it if you want to.
Can you give us an example of a typical loss with a fairly heavy inverter, 12-volt inverter, running how many watts are we really losing in a quality installation?
All right. Things that we figured out, we've got 2 batteries running in parallel. We got about 2 meters of cable going to the inverter, 2 meters of cable coming from the inverter. In between is a shunt. In between is also a mega fuse holder as the primary battery positive power distribution. We found lose about 500 watts when the inverter is running at about 250 amps, which is roughly 2.7, 2.8 kilowatts. So those 500 watts, you can now quite easily say, if you do that for an hour, that's 500 watt hours of energy. A 100 amp hour 12 volt battery stores about 1.2 or 1,200 watt hours of energy. So you see, from that battery, if you would run that for an hour, 40% of that would just be wasted. And all you do with it is, like I said before, heat up the inside of your vehicle. And if you do it too much, heat it up a lot because there'll be a fire. And you really want to prevent that. So that's a good example that I've found. So you can think about it, 2.5 kilowatts going actually into the inverter, going into your induction cooker, whatever it might be. But really from the battery, you get 3 kilowatts. And the 500 watts of that, they're just wasted energy. They're limiting the runtime of the electrical system. And to prevent that, that is really key. That is something that we try to tell people everywhere. You want to eliminate voltage drop as much as possible. Also to your fridge, to the lights that you're running. Because wherever you get voltage drop, you're wasting energy that you cannot use anywhere else. So it's not just about the fridge stopping too early because the voltage has dropped 2 volts and it's below the cutout point. It's also making sure you use the energy that you've got efficiently, because in vehicles, mobile applications, we're limited. We would like to take a whole chunk of energy, but eventually we run out of space, out of money, or out of weight carrying capacity. These are always limiting factors when we do installations. I'm not sure if everybody's aware of that. When you do install DC-DC chargers, the DC-DC chargers are really good at overcoming voltage drop to the unit itself. So supply from the alternator to the DC-DC charger is not that crucial. But from the DC-DC charger to the battery is super crucial. Ideally, you have your DC-DC charger within a meter of the battery you want to charge, because if it's 14.2 volt at the DC-DC charger, it might only be 14.1 at the battery. As the current drops down, that equalizes, but what it means is it will just take longer to charge the battery. And I've seen examples where people have installed DC-DC chargers under the bonnet in the front of the vehicle, but have put a lithium battery in the back of the canopy. What happens is that the charge cycle will actually stop prematurely, the battery will never fully charge, and the customer will always think, well, battery only goes to 70%, and I can't figure it out. Everything works, charge lights work correctly. That's another issue of voltage drop, so it's really important to be aware of just that.
Can I rant a little? Is that allowed? So I think the worst product ever invented in the four-wheel drive industry ever was a solenoid switching split battery system. The problem was they worked, but only just. So a customer who thinks, oh, I'm getting a charge to my battery, thinks it's working, but it's only working. It's working so badly because you've got a connection, you've got a fuse, you've got a cable, then you've got the solenoid and a bad switch inside the solenoid, and then you've got another cable, another link eventually to the battery, which is maybe in the back of the vehicle. So by the time the start battery voltage reaches that, the start battery is sitting at 13.8 volts. What is it at the battery? 12.4. At 12 volts at the house battery, it's a flat battery. So the battery, you could drive from here to Cairo and back. It will never get 100% charge. And if we're lucky, some of them are so bad, it won't even get a 50% charge. That's why I hated that product with a passion, because they kind of worked. And when I was in my, I'm talking about, before 2010, before my first C-Tech DC-DC charger, which changed everything, I bought my second 105 and had the solenoid in it, and I started playing with it, and I could not get a charge to my battery, even though it was in the engine bay. There's a start battery, there's the auxiliary battery. That short thing via a solenoid wouldn't charge properly. So I took out the solenoid, and I just had a cable, and I had a memory. In the evening, pop the bonnet, turn the battery off. That was my split charging system. And it actually worked okay. It worked massively better than this terrible solenoid. And those days were the days that I grew to hate that product for the reasons I've given.
And they really
DC changed everything.
And they really started to fail, those split charge systems, when temperature compensating alternators came out. Because the old constant voltage alternators, they would run and they would sit at 14.4 volts and they'd just stay there all day long, unless you would draw too much power from them and the voltage would drop. But when Toyota brought out the temperature compensating alternators, they would start at 14.2, 14.4 volt, they would heat up, and then they drop to 13.2 volt. And now you want to charge a battery that needs to be charged to 14.6 volt with 13.2 volt at the alternator, plus all the cables and the voltage drops, and then you end up, what Andrew said, at 12.5 volts. And that was about the time when people realized, hang on a sec, I'm not getting anything out of my batteries anymore. So that's just as a little anecdote from that. Our circuit board power distribution, circuit board based power distribution, we say it does matter because you can shrink down the space of your installation. You can have correctly sized current paths every time. It is pretty much like copy, paste, which I think would be the ideal world scenario of how you can do installs in general, right? You know, this works. I know this works, we've done it before, and now I'm just taking it and I'm just gonna do it again and again and again and again. Because you know the outcome of that every time. Another good thing is that the connection logic of these circuit boards is printed onto the circuit board itself. So to a degree, the product is its own product manual, which is great in the workshop because nobody wants to read a product manual. You only go to the product manual once you've stuffed up and you go, hang on a sec, we can't get any further. Here's their manual.
And that is when we turn off the cameras. Cannot show. We're men, we know how to do it.
Yeah. It's all in the edit.
Secretly. Look at the manual.
Another thing that I want to touch on, because if you have the circuit board still cycling around, have a look at the connectors on the circuit board. The connectors, the screw type connectors that you usually use on Victron equipment, and the way they usually work is that there's a screw coming from the top and it squashes the cable and it breaks the strands and eventually the cable falls out. It overheats because of voltage drop, and it's terrible. The only way around it is that you use ferrule crimps, but that takes time again. So what we've done is, and it's not a screw that squashes onto a cable, it's actually working like a crimp. So there's a lifter on the bottom that lifts up, and it's like doing a crimp with a hex crimper. But the good thing is that crimp you can undo with a screwdriver. And it's also really important that you actually do not use ferrule crimps, because they reduce the surface area in between the connector and the cable you put in. You just want to take the insulation of the cable, put it into the connector, tighten it, torque it. There's torque settings for these connectors. And then, very important, on the brackets that are around, there's little T-bars on there. And what you do is you put a cable tie around the cable, hook it on the T-bar, tighten it, cut it off, and now you got pull relief. If anything happens, anybody's pulling on the cable, it's rattling because of corrugations, it's never on the connector itself, it's always on the bracket. There's another reason why those brackets are relatively solid, and probably more solid than they have to be, because they're an integral part of the pull relief system to make sure we're not wiggling on the cable. Because if you do that all the time, what happens is the copper, with every movement, squashes together a bit more, a bit more, a bit more. The tension isn't there, it should be there anymore, and eventually either A, the cable falls out, or B, we get voltage drop, we get heat buildup, something starts to bubble, eventually catches fire. I've touched on that screwdriver operation only, which I think is quite important. I had a lot of first-year apprentices in my workshop, and it took, let's say, 3 to 6 months before I would trust them to do proper crimps and heat shrink. It seems trivial, but a lot of people still struggle, and the cable is half out and it's not de-insulated properly, the heat shrink is not on properly. To connect cables to that, you need a screwdriver and a side cutter. And that's it. That's all the specialized tools that you need. And that will give you, as a workshop, but also as a DIY person, consistent, repeatable, and professional terminations. Because another thing with this is, like, you usually have the showpiece of your installation. There's this one part, we always called it the snake pit in the workshop, where all the cables come together. And that's the part where you take your main technician, you stick him in there for about 8 to 10, 12 hours maybe, and he makes sure everything's terminated in a nice way. Everything is done properly. You go from big cables to smaller cables to even smaller cables, the right fuses in between. He knows how to do that. Now the problem is that technician leaves, you have to have somebody else there that does that final connection, also knows how to do it in a way that people actually want to look at it, because that's usually the part that you see of the installation. And it took us about a year or two to train a technician up to be at the level where they could do presentable work. The first year apprentices would just run the cable from A to B and make sure they don't chafe anywhere. We found with the Egon system, it takes us about 2 to 3 months tops, and you can have a technician in there if they already knew sort of what they were doing before. If they're very fresh, they've never actually touched a cable before, it will take a bit longer. But you can put that technician in the spot, into the snake pit. You always use the same layout of your installation. Andrew, do you want to explain what a DC hub actually is, what it does, what's connected to it?
So the idea was one central unit, and in the early days when we were trying to explain it to people, imagine one unit where everything is connected. So the word everything.
Except the inverter.
Except the inverter, but that's not the case with 48 volts, and we're going to get to that now, because even 48 volts, we even have the inverter through the board. So all the chargers, all the solar, the panels, the MPPT, the DC-DC, even if you have 2 DC-DCs, 2 batteries, everything. There's no bus bar anymore. All that bus bar, all that cabling to the bus, gone. Because everything is 2-point. So that was the kind of the challenge we had in introducing it, is now, what do you mean by everything? If it's on your list of components of your build, it goes wired directly to the DC hub, everything. So my MPPT, yes. And so does that, yes. So that was kind of a challenge for us, for people to get, and then the workshops, when they got hold of it, where do I put there? Where do I put there? It says so on the board. Regulated solar, unregulated solar. I need to run my ARB twin compressor, 80 amp output. My fridge. I got 2 lights. I got a water pump. There it goes. Everything goes into the. So the idea was, again, one place to fault find, one place to run wires to, and if you want to add something afterwards, where are you going to run it to? DC hub. That was the
idea, yeah.
Mental behind, and it works.
There's also a way to get away from wiring harnesses, because wiring harnesses are quite complicated to make. They take a lot of time if you make them in a workshop environment, and they're quite expensive if you get them made by a professional wiring company that creates professional wiring harnesses. So the idea of this is that you can use for almost anything you connect to it a twin core cable, because we all got twin core cables in the workshop. Or you use multi-core cables like 5-core, 7-core trailer cable. If you need even more, I can highly recommend using Ölflex or lap cable. They're also called industrial control cables. I'm not sure if you guys are familiar with them. They've got gray sleeving on them, and you can get them from 2-core up to 192 core. All the cables in there are black, but they've got numbers on them from 1 to the very end, and always a green and yellow cable in it. So we would, instead of using harnesses, we would use control cable, multi-core, so switches in the dash instead of running individual cables, we run from our snake pit a 12-core cable to the dash. Do a roof installation, run a 12-core cable into a junction box of the roof. We only need 5 cables, that's cool. But if the customer comes back, wants an extra solar panel, extra light, we don't do everything again, we just add to the multi-core cable. So make the whole thing future-proof. Customers love it, and you say like, look, it costs you about $50 more for the cable run, tops. But in the future, you save massively because we don't have to take your whole vehicle apart again to do another cable run for another light that you might want to install. All right, but this is the first product that we've designed that Andrew just talked about. So the idea of that is from 2019. We've changed things a fair bit in the process. You could pretty much call this the classic DC hub example. Single DC-DC charger, normal output, solar connections. I get to the nitty-gritty of that a bit more. So what you've got here is, this is a 150 amp house battery connector. So you can put 150 amps through the circuit board. And you probably see that I've put not amp hour. About every week or two, I'm receiving an email where somebody says, what if I want to connect a 200 amp hour battery to this? And then I'm usually explaining, look, there's a difference, amps and amp hours. Everybody talks about a 200 amp battery, 300 amp battery. But what we really want to say is it's a 200 amp hour battery. So the difference is amps is the current, the rush, the water flow. Amp hours is the amount of energy stored. So you can connect 10,000 amp hours of battery storage to this. Just make sure you use the 150 amp fuse to protect the board. And furthermore, we've got here, this is the start battery connection. Like I said, house battery, start battery. And then we have got a solar input here, so you can use an unregulated solar panel. And on these connections here, you can connect the DC-DC charger with an inbuilt MPPT. And that's it. That's all you have to do to connect your charging system. All the grounds are looped on the board. They're all connected together. You've connected to ground of the vehicle because you've run a twin core cable to the start battery. The start battery is grounded to the vehicle. You've got ground to your house battery. And the system will start to charge as soon as you crank the engine or your solar panel is exposed to the sun. If you now want to add loads, you've got 10 25 amp connectors for fridges, for lights, charge ports, whatever you want to use them for. On here you've got 2 40 amp outputs that you can quite easily use if you want to have a switching system, third-party switching system. There's so many different variations of switching systems. Egon makes one as well. It's called a relay hub, but it's completely up to you. This is compatible with any DC-DC charger on the market. It is compatible with any switching system on the market. All this is just doing your power distribution. And over here you've got an 80 amp output to run higher appliances like your ARB twin piston compressor, for example. You probably see on these boards we are still using what is called a maxi fuse. The reason for that is that we started with the maxi fuses because internationally, and I've learned not in South Africa, they're quite foreign here, these are readily available everywhere. In Australia, you can buy them at service stations, together with the smaller blade fuses. But in the newer alterations of our products, we've gone away and we used MIDI fuses. And you will see that your high amp inputs and outputs have got double fuses. The reason for that is if one of the fuses slightly loses contact, it will immediately overload the other fuse, and then it will overload the fuse that has slightly lost contact, and the two fuses protect each other. So if you want to put a 40 amp DC-DC charger to this unit, what you do is you want to fuse it with 60 amps, you put 2 30 amp fuses in here, and they protect each other from overload, because a lot of you guys have probably seen maxi fuses in engine bays, in these fuse holders, very crispy, and all you can do with them is cut them out and replace them with a MIDI fuse. The twin fuse setup prevents that from happening. Also really important for you guys to know, all of these are inputs and outputs. So if you want to use an extra solar regulator or extra 240 volt, 212 volt charger, you can just put the charger into one of these connectors, put a fuse in, and it also now feeds into your start battery. That's the general logic of our circuit board. Not a lot has changed. The other products are just slight variations of that. And here you can see a connection example. So this is probably the most basic setup you can run in a vehicle. All these wiring diagrams are also on our website at egon.com.au. You will find compatible with Egon, and you find red arc diagrams, Victron diagrams, Enerdrive diagrams. We're expanding these to different product ranges, and we have these as your sample wiring examples. You will find that there are cable ratings in there, and I've learned that nobody in South Africa knows what 3BNS means. We will have some tables that will actually say 3BNS is 25 mil, is 35 mil, is whatever it is, so that we translate that in a bit more international way. And the way this setup works is you've got your start battery, you've got a fuse, start battery to the board, house battery to the board. Here you have your start battery through a fuse with ground to the board. Your solar panel to the board. DC-DC charger to the board. If you want to run a big inverter, you have an external fuse that runs to the inverter, or your grounds run through the shunt, and that is your charging system setup. All you need to do now is connect loads, put fuses in, your system is ready to be commissioned. Just checking in, does that make sense?
So you've got the start battery connected and
Yes.
DC-DC.
Yes.
So does the circuit actually flow through the board to the DC-DC?
Correct. So the way this works is that this input here is directly connected to this output here, and the solar input here is directly connected to the solar output there. The reason for that is that we don't want to have that connection external somewhere, soldered together. We want to be able to access that with a multimeter in case you want to do fault finding. That's the reason we're actually channeling it through the board. Because otherwise you have to go, oh, hang on a sec, where's that cable going? Where's it actually connected? We want to prevent that, because that way the fault finding of the system is completely standardized. You can go through the same procedure every time. Even if you use different components, the idea behind it is always the same. This is pretty much the bigger brother of the DC hub. The only difference is that this is capable of running 2 DC-DC chargers. Outputs are the same, and you can see that this is already a newer generation board that is at the moment being sold here in South Africa through Tricara as well. And we've put MIDI fuses on the board, also for the output. So the difference here now is that you've got an 80 amp output, and the 40 amp output of the other board on this unit are also 80 amp outputs. So you can run heavier appliances.
Why would you use 2 DC to DC chargers?
Reason for that is, imagine you're running, and it's not quite uncommon, a 400 amp hour lithium battery bank. Now, if you use a single DC-DC charger, a 50 amp DC-DC charger, the recharge time, ideally, in an ideal world, is 8 hours. 8 hours of driving is often quite a long time to recharge that. So what you can do is, instead of using one 50 amp DC-DC charger, you use 2 50 amp DC-DC chargers. You reduce that charge time by half. Now you can recharge your 400 amp hour battery bank in 4 hours instead of 8. So the idea is that you use multiple DC-DC chargers, but I wouldn't recommend more than 2, because otherwise it gets complicated with actually supplying the chargers. And generally in any car out there, as soon as you go higher than 50 amp DC-DC chargers, you will have to upgrade the alternator. So this is for really heavy-duty, high-end systems. That's probably as high-end as you can go with 12 volt to have a 100 amp DC-DC charger. You generally need a 250 amp alternator for that. That needs to be directly wired to the start battery through a 50 mil cable with a 300 amp fuse connected to it, and that will be capable of supplying those DC-DC chargers. Because keep in mind, an alternator that is rated at 250 amps, in reality, when it's at operating temperature, you'll be lucky to get 220 amps out of it, and that's at high RPM. In idle, you get about 40% of the 250 amp, and that is not a great deal. So even for these systems to charge at 100 amp, If you've got a 70 series Land Cruiser, you would have to press the high idle button to actually get 100 amp into your batteries. And if you go a lot larger with 12-volt alternators, the problem is the amount of energy that you lose from the alternator to where you actually want to charge. You lose as much energy as you actually get out of the unit itself. And you need 2 cables for battery positive that are about the size of my thumb. So we're talking about a 120 mil cable that you need for that, or at least a 95 mil cable. And eventually it goes to a point where it gets just too ridiculous, because you need to carry a trailer just for the weight of all the cables that you've put in your car. And there's a limit to this.
Yeah, I think, Heiner, if you could just perhaps elaborate a little bit more on the actual alternators from vehicles.
Yeah.
From the Land Cruiser at 130 amp alternator, the vehicle's using more than 50% of that alternator at any one time. You turn your aircon on, you put in between 12 and 15 amps. That's what I've noticed from mine. So you actually probably only got a usable 30 amps or 30% out of that 130 amp alternator.
That's
so
correct.
even if you've got a 50 amp DC charger, you're not getting a full 50 amps from the alternator. And I think you look at the newer cruisers. That's working now. Thank you. You look at the newer cruisers, I think the 2.8's got an 80 amp alternator. That's actually correct.
The newer ones have got, I think, 135 now. The older ones used to have 80.
I mean, that's where the curtains are in all the system. Like everybody, you can put massive DC chargers in, but we forget about the actual supply, the origination supply.
Yes, the energy has to come from somewhere. It's not just being created out of thin air, unfortunately.
We all think we put 49,000 factory in. We've got all these systems, we've got air fryers, we've got factory cookers, etc., etc. Then we suddenly realize we can't charge. We don't have a big enough DC system. So you put 2 DC to DC chargers in. Now you don't have enough alternators. Supply the 2 DC to DC chargers.
Yeah, so when you design these systems, you have to start from the power source, think through all of it. Where does the energy come from? How do I transport the energy? Where does it go into? How much energy do I actually use per day? So a good way of laying out systems is that you usually start with a list where you say, these are the components that I'm going to run. This is how much energy that is going to take every single day. And then a customer knows, like, look, okay, cool, we've got a figure here. That's what we have to work towards. I would usually tell customers, if you can, be power independent for 48 hours. Because wherever you're camping and you're not getting any charge from solar panels for 48 hours, you probably want to leave, because the weather will be absolutely miserable and you want to find a different place to camp at. And then the next question is going to be, how long do you want to stay in any one place? If it's longer than 2 days, you have to make sure there's solar panels that can actually put the power back. Or if you say, like, I'm usually driving every day, you have to make sure the DC-DC charger system is big enough to replenish the energy that you've taken out with the driving cycles that the customers are actually driving. A lot of customers say, look, we drive 2-3 hours every day, so you have to make sure the DC-DC charger is powerful enough to put the energy consumption back into those batteries in the 2-3 hours of driving time. That's how we would always calculate systems for customers. And at the end, it's not about, I would like that DC-DC charger and I would like so much of solar and that regulator. It would be like, well, you should be using this because that will make your system work. Customers would usually come into the workshop for us with a list of products about that long. And after they've told me everything about what they wanted, would say, like, okay, look, let's see what you actually need. And quite often it was a lot less than what was on that list. And some items were like, but I really like that. And no, that's fair enough. We all like certain things. But it's important to let a customer know what are your actually needs, what do you actually really need to make that system work when you're out in the field.
So I think lately what I've done recently, the introduction of the price from Egon, we built a little program which does exactly what Heiner's been explaining. So talk the customer through all the loads that they've got. We can actually plug it into the little program. It then splits out obviously what the current draw is, what the peak current draw is, and it can determine what your surface is going to be and what you need in terms of charging system, batteries, etc., etc. And we do offer that as a service.
So that is like a planning service, and it's not just for workshops. You can use it as a workshop, But as a DIY person, you can also use that to find out what do I actually need from my system. And the calculations behind those are not very complicated, but it's better if you can use an interface, and it is an Excel spreadsheet that the guys from Tricara have made. And we will adopt that to our website as well, because having a guide on how to design systems is so important, because then you don't have to guess, is this going to be okay? You can tell your customer, look, from what you've told me, this will work. We can guarantee that. It's a massive step up from just guessing, I think that will work. Let's build it as big as possible. And like I said, these are all input-output connectors. But what is really important when you are building a dual DC-DC charger system, this is your start battery. It feeds into these two ports of the circuit board. And under all circumstances, you have to make sure that instead of running one cable, please run two cables. Because DC-DC chargers never kick in at the same time when they're voltage sensing. So if you just use one cable and one DC-DC charger kicks in and starts to charge at 50 amps, it will create voltage drop on that line. And it can very well prevent the other DC-DC charger from then kicking in, because it thinks, oh, the engine has stopped again. So I'm going to check again in 60 seconds if the engine has now fired up. But eventually, the other DC-DC charger is going to stop to check what the voltage is actually like and if it can keep charging. And in that time, you get the other DC-DC charger kicking in, preventing the first one from restarting. And the way to get around that is that instead of one cable, you use two cables. So each DC-DC charger has got its own cable with its own voltage drop. And that way you don't get these issues with the fluctuating DC-DC chargers, which I think a lot of people, you've seen that in your setup. And that is the way on how to prevent that. So this is with the DC-DC dual. This is a standard system that we would say you can build. Here's the case with Victron Orion XS DC-DC chargers. The way this works now is that when the alternator is running and charging the start battery, the DC-DC chargers kick in and they can charge up to 100 amps into your house battery. See, the house battery is connected here to the board itself. But now on top of that, you can also have quite a big solar array. If this is, let's say, a caravan or quite a big truck build, or it might be a big troopy build or really big canopy build. So you can have 400, 800, maybe 1,000 watts of solar on the roof and have another 50 amp solar regulator. That can now feed into the unit itself as well. And now you get DC-DC charging and solar on top of that. With that system, when it's maxed out, you can get up to 150 amps charge into your battery itself. That's pretty much the limit, because the big connector on the board can't handle a lot more. But when you're stationary, you can install a secondary solar regulator that you use for a plug-in solar blanket. Because when you're stationary, your DC-DC chargers will not work. So in this system here, you've also got a big 3 kilowatt inverter. This is our Egon relay hub switching system, directly wired to the board. You've got a monitoring system here, and that is your typical installation for a DC hub dual. This is called a DC hub nano. This is our new generation board. There's also a DC hub dual version of that we've been passing around. Follows the same logic, more compatible with Victron, these boards. So here you've got the same things that you had before: 150 amp house battery, start battery connection, and your next generation solar input connection. I'll explain that in a minute. You've got 3 80 amp outputs on this tiny board and 5 25 amp connections. You've got, like on the other boards, the built-in fault finding with the LEDs and obviously the inbuilt bus bar. And I'm not sure if you've seen it yet, but it's shrunk down a lot. The size of that is only this, because we found that a lot of people don't install massive systems. They might have a drawer system installed in a 200 series or a very simple canopy install. And they were always saying, like, look, we love the product, but it's too big. If you could just be smaller, makes it also more affordable and easier to install. And that's why we came up with this board. And this is a typical installation you could do with this tiny board. So it might look tiny, but what you can do with this is you can use an Orion XS 50 amp DC-DC charger. You can use a 50 amp solar regulator, and you can use this board to pump 100 amps of charge into your house battery. And the way that you can do this is now, you've got your start battery here, and you've got your DC-DC charger like before right here. The start battery is linked to the input of the DC-DC converter. That makes that side work really easily. But what we've done now is you can wire your solar panels directly to the MPPT, and then instead of wiring it to any of the other outputs, the solar input here is now regulated and unregulated. So means if you use an external MPPT like this, you can put this fuse in, and now this connection feeds directly into the house battery. If you use a red arc DC-DC charger with an inbuilt MPPT, you leave the fuse out, you put the extra cable in to the red arc DC-DC charger with the internal MPPT, and now the DC-DC charger feeds through this fuse into the house battery, and you leave this out. Makes it a lot more compatible with Victron products or any other products where you got external MPPTs, and it leaves these three connectors here completely available for full ATM capacity. So you can use this to actually run one of the new ARB brushless compressors, 60 amp fuse, 60 amp fuse, and it can run directly off the circuit board. Leaves you space here for a switching system. Now that can be an Egon system, that can be any other switching system. I've seen that some of the workshops here use these little touch panel screens with the data connection cable. You can use that for it. Works very easily. And you can wire in your 3 kilowatt inverter. You've got your shunt in your line here. And instead of having to build a quite large power distribution system with bus bars, fuses, pre-fuses, almost anything now just runs through that little circuit board, and your workshop time probably drops from about 7-8 hours to about 2 hours to do the final termination of the system. And the new DC hub dual that we've got works in exactly the same way as this unit, but instead of having one DC-DC charger connection, it's got 2 of the next generation DC-DC connections or charge connections. And instead of having 5 25 amp outputs, we got 10 25 amp outputs here. That's it for our products, really, except for...
We're going to do what everybody's really excited about, and I'm probably overly excited about it. 48 volts. So I'll give you a little bit of history. So we had, these were going really well, and we were having a fantastic response. And so we thought, okay, perhaps we've solved one big problem. Okay, what's the next big problem? We discussed it. And what's the next big problem with electrical and camping is charging the battery.